General Physics 1 is brought to you by Physics Classroom. Let's continue exploring motion. Moving on to the next important concepts of kinematics. This is about acceleration and uniformly accelerated motion. Imagine yourself driving your bicycle along the road when suddenly a man crosses the road. What would you do? Definitely you step on the brake. What happens to the bicycle as you step on the brake? When an object changes its velocity, the object is said to accelerate. Acceleration is a measure of how fast the velocity changes with respect to time. This means that a body accelerates whenever there is a change in speed, a change in direction, or a change in both the speed and direction. Acceleration is expressed in units such as meter per second squared, kilometer per hour squared, meter per minute squared, and many others. Blood flow also exhibits acceleration. When the heart pumps, the blood is pushed away from the heart. The sudden surge or push to the blood makes the flow of the blood change in speed or direction. Acceleration is expressed by the formula Take a look at the parachuters. Are they falling? Are they moving horizontally? Motion comes in two forms, linear motion and curvilinear motion. Linear motion refers to the movement of an object along a straight path. Examples of these are vehicles and other objects with a constant acceleration, and free fall. Curvilinear motion is the motion of bodies along curved paths. Projectiles and objects moving along curved paths are some examples. If a vehicle maintains a constant or a uniform change in its velocity, in a given time interval along a straight line, then the vehicle is said to have a constant acceleration. Its motion is known as uniformly accelerated motion. This constant acceleration could be derived using the equation. Solving for the final velocity, we have the first kinematic equation. Since the object is undergoing uniform acceleration, its velocity changes uniformly, with time, from initial velocity to final velocity. As a result, the average velocity is simply the average of these two values. If we substitute the value for velocity, given by equation A, for velocity in the equation, distance equals velocity times time, we obtain the second kinematic equation. And again, from the equation, distance equals velocity times time, we replace t equals v sub f minus v sub I, divided by acceleration, by its value from equation 2. Solving for v sub f squared, we get the third kinematic equation. Replacing v sub f by its value obtained from equation 2.1 to the equation. Finally, we get the fourth kinematic equation. We now have equations that apply to uniformly accelerated motion. They are sufficient to describe motion in any ordinary situation in which acceleration is uniform. They are likewise known as the four kinematic equations. And now here is table 2.1, the four kinematic equations. Before we proceed to solving problems involving uniformly accelerated motion, here's table 2.2, that will serve as a brief guide to help you translate problems involving motion. If the question is, when, it means that you need to solve for the value of time. The question, where, indicates that you have to find the distance. Starts from rest. Implies that the initial velocity is equal to 0. If the question is, how fast? You are required to solve for the value of velocity. How long does it take? This question means that you have to solve for the value of time. How far is another question, which means that we have to determine the distance. If it says comes to a stop, it means that the final velocity is 0. Now that you are already guided, let us solve problems starting from example 1. A car moves with a speed of 25 meters per second. It slows down and comes to rest 5.5 seconds later. Find how far did the car moved within the 5.5 time interval. Example 2. A plane starting at rest at one end of a runway undergoes a constant acceleration of 4.8 meters per second squared for 15 seconds before takeoff. A. How fast is the plane at takeoff? B. How long must the runway be for the plane to be able to take off? Example 3. A mother pushes a stroller from rest until it accelerates at the rate of 0.500 meters per second squared. How fast is the stroller moving after traveling 5.25 meters? Again, be reminded that learning is by doing. Perform the concept understanding and self-activity. To further enhance understanding of the concepts, try to figure out the best answer to each of the questions. Number 1. The diver, the skater, and the runners are accelerating. Can you identify the change in motion in each of the given examples? Number 2. If a tennis ball has a zero velocity at some instant during a game, is the acceleration of the tennis ball necessarily zero at that instant? Explain and give example. Number 3. If a passenger bus is traveling on a straight road with a negative velocity and a positive acceleration, is its speed increasing or decreasing? For the self-activity, solve the problems below. Number 1. A bike accelerates uniformly from rest to a speed of 7.10 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. Number 2. An engineer is designing the runway of an airport. For the planes that will use the airport, the lowest acceleration rate is likely to be 3 meters per second squared. The takeoff speed for this plane will be 65 meters per second, assuming this minimum acceleration. What is the minimum length for the runway? Based on what you have perceived from this activity, how important are the 4 kinematic equations in solving problems involving uniformly accelerated motion? Thank you and learn in constant motion. Move forward to a positive direction.